So welcome back. Now we are moving on to the next lecture, which is basically the next generation of MapReduce. How do we further improve the MapReduce framework, leading to a whole second generation of it? So basically, we are right here, right in the processing. So last week, well, technically today, we studied MapReduce. We saw that this whole thing with the slots, the nodes and the slots corresponding to the CPUs, cores, the tasks, the function calls, and so on. And we saw that we have the job trackers on the same machines as the name nodes, the task tracker, which is basically responsible of the map slots, reduce slots, and the calling of the map and reduce functions and combine functions. They're co-located with the data nodes. Now you know why, because the MapReduce slits corresponds to the HDFS blocks. So that's why it's designed in this way. And now if we look at the responsibilities of this node right here, what does it have to do? Well, it has to do a lot of things, even though I didn't say much about it. It has to manage the resources of the cluster to know what nodes are connected and available for slots. It has to schedule and decide on the attribution, the hash function, and so on. So it schedules the whole thing over the cluster. When a slot asks for a task, then it points it to the next task. It needs to monitor, because if a map slot fails and crashes, then the job tracker needs to contact another machine and say, okay, now this failed, so now you need to take over that map task. So you throw away the crashed one, and then another machine is going to execute it. So it's fault tolerance, right? It doesn't matter if something fails. Of course, if it's a mapped task that fails, it's easy. If it's a reduced task, it can be more tricky, because in the worst case, you might need to start the job all over again. Right? If in some cases, if you cannot recover the intermediate data anymore, then you have no other choice than to start all over again. But basically, it requires monitoring and job lifecycle, which is making sure that the job gets executed, even if some of the machines actually crash, and that makes it fault tolerance. Do you see that that's a huge amount of responsibilities for a single machine, right? And as we say, jack of all trades, master of none. And so it means that there's a bit of a danger and a single point of failure in here, and a bottleneck in terms of efficiency. So it brings a few issues. So the first version of MapReduce that I showed you was pushed all the way to 4,000 nodes and 40,000 tasks. And then a wall was reached. Basically, when you reach that, then it was at its limits. A second problem we have that I mentioned is the bottleneck. The job tracker with so many machines can be overloaded, and then that slows down the whole thing because of the monitoring and recovering and so on. The third issue that we have, if the computer agrees to move on, is that this job tracker takes both care of the scheduling of the tasks and of the monitoring of the failed machine. So that's two things to do. A fourth issue is that during the map phase, all the resources attributed to reduce slots are just doing nothing. It's just unused virtual cores. And the same during the reduce phase, then the map slots become idle. They are not needed anymore. So we are wasting a few resources in there. And number 5, yes, so that's what I mentioned. So issue 4 is that it's statically allocated. You decide statically at the beginning, these are my mapping slots and these are my reducing slots. And number 5 is that they are idle, right? So you basically keep some of them idle during each phase. Who is with me on these problems? Okay. And so, of course, people wanted to solve these problems. There's very smart engineers that thought we need to do something about this. And so what they did is that they designed a completely new system. Okay, this one is dying, no more batteries. And they called it yarn. So whenever something starts with YA, do you know what it means? Yet another, exactly, yet another resource negotiator. That's called yarn. Yarn is basically going to solve that problem with yet another sets of, that's a fourth one now that you need to learn, resource manager that's going to run on the coordinator node, and node manager that's going to sit on the machines. The goal is to manage the resources, the memory, the CPU, and so on. And it's a little bit like small virtual machines, if you want. So we have now these logical resources called containers that correspond to a CPU core or a few CPU cores and a bit of memory that are logical parts of the resources of the machine that are used for the execution. And so the way it works on the high level is that when a client wants to execute a MapReduce job, they are going to connect to the resource manager and say, okay, I would like to execute that MapReduce job, pretty please. And then the resource manager says, oh yes, but I don't want to take care of it because I already have too many things to do. So the resource manager is going to schedule one of the containers and make it the application master. And it's going to delegate what used to be done by the job tracker. It's delegated to the application master, which is now sitting on one of these worker nodes. And it's no longer dealing with the MapReduce job. It just delegated. So now the application master, who is responsible for the MapReduce job, is going to react by saying, oh yes, but I can't do it on my own. I need plenty of more containers to do the mapping and the reducing, right? So he's going to connect back to the resource manager and ask for resources. So the resource manager is going to say, okay, you can use all of these containers, which are just CPU cores and memory, and then you can do your thing. And that's dynamic. It can only request, for example, at first, just for the map slots, right? And then it forgets about the rest. Now we have our MapReduce job, but the job tracker and the task trackers are now logical, one level of abstraction above. And when this is done, it can request more resources for the reduce slots with further containers. So that's the idea of how we modify the architecture. So it means that now the coordination node that is the bottleneck only deals with the scheduling of resources. It just says, you know, these are the CPU cores and memory that you can use, while the actual coordination of the job, the MapReduce job, is delegated to one of the containers. So now we can have 5 MapReduce jobs in the same cluster. And in fact, Yarn is more generic than MapReduce. You can have also Spark and MPI and plenty of other technologies that use Yarn. Yarn is just here to allocate CPU and memory fairly to whoever is using the cluster. Who is with me? Right? So you see what's new is just that now we have this more logical abstraction with a container instead of the job tracker and containers instead of the task trackers that are just now virtualized, so to say. So when we talk about containers, we typically mean a few CPU cores and memory, but you could also consider that a bit of disk I/O bandwidth is part of this container as well. A bit of network bandwidth is part of it. But the disk of the network is work in progress. I don't know if they made a lot of progress on that, but mostly think of the CPU cores and the memory, right? Because organizing a prorata of the disk I/O and a prorata of the network bandwidth is trickier to organize. So basically, a container is that. It's a logical allocation of a few cores and a bit of memory. For example, 4 cores and 10 gigabytes of memory, right? Who is with me? Right, okay. And so the idea is that, and now I reduced the number of slides compared to previous years. That used to be a very long course, but I squeezed it a little bit to focus more on the data parts. So the scheduling means that now this resource manager is going to allocate the resources dynamically to everybody, and it has a whole scheduling set of scheduling algorithms that allow to assign the resources to the cluster, even if 100 people are using the cluster at the same time, right? So it makes a lot of sense at the scale of a company that has plenty of users. For example, at CERN, they have a Spark cluster and people can use it. So it's typically using this kind of allocation. Then I have, just checking the time, we have a few minutes. Some things that should be familiar, because we have this architecture with the resource manager and the node managers centralized, just like name node data nodes or HMaster region servers or job tracker, task tracker. Well, guess what? We have heartbeats. Again, all these machines connect to say they're still alive. And there's some information that is basically uploaded to in order to monitor. And then there is some way for the resource manager to keep track of the healthy nodes and the unhealthy nodes, right? So it knows what has crashed, what hasn't crashed. And so it's able to monitor the machines like that. And so now, dealing with the fault tolerance, for example, I have a MapReduce job and one of the map slots just crashed. That's no longer the problem of the resource manager. That is the problem of the application master. Remember, the application master was this one. That's their problem to deal with relaunching a failed task. So we offloaded some of the workload from the coordinator node to one of the worker nodes. Who sees that? Right? Very good. So now we remove that bottleneck. So in summary, we now separate between scheduling, which is done on the top level by the resource manager, separated from the monitoring, which is done by a container on the worker nodes to whom we delegate that. It enhances the scalability. It enhances the availability of the cluster. It also makes it multi-tenant, meaning that multiple people can use the same cluster at the same time, and you can control the resources that they get. So that's called multi-tenancy. Right. Yarn is very important. It's orthogonal to MapReduce. MapReduce version 2 is basically the modification of MapReduce where we replace the job tracker and the task tracker with the use of Yarn. That's MapReduce 2, right? And Spark, which we are going to start studying tomorrow, also runs on Yarn. It uses exactly the same framework for getting the containers and delegating to the application master and executing the tasks. So that was Yarn, yet another resource negotiator. And tomorrow I'll introduce you to Spark, which is the next generation of MapReduce frameworks. Thank you very much, everybody, and see you tomorrow.